Welcome to The Explainer. Today, we're diving headfirst into one of the most critical and high-stakes arenas in all of medicine, the battle against bacterial infections. We're going to unpack the tough decisions clinicians are up against every single day. So here's our game plan. We're going to walk through the logic of an antimicrobial consult. We'll start with that urgent need to treat an infection you haven't identified yet. Then we'll get into the nitty-gritty of our antibiotic toolkit. See how lab data helps us zero in on the target, face the tough reality of resistance, and wrap up with the one strategy that can secure our future: stewardship. All right, let's get into it. We're starting with what we're calling the Empiric dilemma, and that subtitle says it all: a calculated bet against time. Just picture it. You've got a patient in front of you. They look septic. The clock is absolutely ticking. Every single choice is this high-wire act, balancing between moving fast and having all the facts. This quote just nails it, doesn't it? When you're dealing with something like sepsis or meningitis, every hour you delay treatment, the patient's prognosis gets worse. You have to make a move against this unknown enemy with what is, frankly, incomplete intel. It's the pure art and science of medicine, making a highly educated guess when the stakes couldn't be higher. Okay, so this lays out the two big strategies we're constantly juggling. On one hand, you've got empiric therapy. That's your broad net, right? You cast it immediately, hoping to catch the most likely culprits. On the other hand, there's targeted therapy. That's your precision strike, your scalpel, which you can only use once the lab has identified the bad guy. Honestly, the whole game in good antimicrobial practice is making that jump from empiric to targeted as fast and as smartly as you possibly can. So how do we make that first bet, that empirical choice, an intelligent one? Well, it is definitely not a blind guess. It's a decision that has to be rooted in a really deep understanding of the tools you have, the antibiotics themselves. Knowing how they work and who they work against is absolutely essential. This table really helps organize our thinking. Look at how these different classes go after totally different vulnerabilities. You've got the beta-lactams and the carbapenems. They're like a demolition crew, just hammering away at the bacterium cell wall. Then you have something like the fluoroquinolones, which are more like saboteurs, getting inside and crippling the DNA replication machinery. And the macrolides, they just gum up the works at the protein factory, the ribosome. That link, right there, between mechanism and spectrum, that's the secret sauce to matching the right drug to the bug you think you're fighting. And this really gets at the heart of why precision matters so much. You know, that sledgehammer approach. Sometimes you have to do it at first, but it comes at a huge cost. It puts this immense selective pressure on bacteria to become resistant, and it causes a ton of collateral damage. You wipe out the patient's own good bacteria, their microbiome, and that can open the door to all sorts of other problems. So you see, making that initial empiric choice is anything but random. It's a very logical, step-by-step process. First off, where's the infection? A bug causing pneumonia is probably different from one causing a UTI. Step 2, what's happening locally? What does our hospital's own data, our antibiogram, say about resistance patterns? Third, is the drug even going to get where it needs to go? You have to think about tissue penetration. And finally, what about this patient? Allergies? Other illnesses? How well are their kidneys working? It's like running a clinical algorithm in your head for every single case. Now, while we're busy making that educated guess, the microbiology lab is working hard to give us the actual data we need. And that data lets us pivot from guess to know. The key to that whole transition is a concept that is so important: the clinical breakpoint. The first number the lab gives us is the MIC, the minimum inhibitory concentration. In simple terms, it's the smallest amount of drug needed to stop that bug from growing in a test tube. It's a direct measure of how vulnerable that specific pathogen is. I like to think of it as the lab asking the bacteria, so, are you going to make this easy, or am I going to have to bring out the big guns? But look, an MIC by itself is just a number from a lab. To make it clinically useful, we need context. And that's exactly what clinical breakpoints give us. They are the official thresholds that combine that lab value with pharmacology, predicting clinical success in a real person. This is what lets us translate that number into one of three critical letters: S for susceptible, R for resistant, or that very important middle category,
I for susceptible, increased exposure.
Okay, time for a quick pop quiz to see if you've got it. You have a patient with an E. coli UTI. The lab calls with the result. The ciprofloxacin MIC is 0.5 milligrams per liter. Take a look at the table. How are you going to classify this bug? S, I, or R? The answer is I, susceptible, increased exposure. An MIC of 0.5 for Cipro falls squarely in that I category. Now, this is a really important concept. I doesn't just mean intermediate. What it's telling you is, hey, you can still win this fight, but you need to make sure you get higher drug levels at the site of infection. You could do that by increasing the dose, or, in this case, by knowing that Cipro concentrates really well in urine, making it a perfectly good choice for a UTI, even with this MIC. It's where pharmacology and microbiology shake hands. And, well, that unfortunately brings us to the much more serious topic of resistance. Yeah, this leads us right to what is, without a doubt, the single biggest challenge in infectious diseases today. You could even argue it's one of the greatest threats to all of modern medicine, the constant and frankly accelerating evolution of antimicrobial resistance. And let's be clear, this is not some far-off theoretical problem. This is happening right now. Look at ciprofloxacin, a real workhorse drug for gut infections. Recent data shows that 21%, more than 1 in 5, human salmonella isolates are now resistant. That means for every 5 patients, there's one where a key drug might not work. And if we look at E. coli, one of the most common bugs we fight, the picture is just as worrying. This is data from patients with serious invasive infections. Resistance to ampicillin is over 40%. But what's really alarming is seeing resistance to our cornerstone drugs like Cipro and third-generation cephalosporins creeping up towards 10%. These aren't just numbers on a chart. Each one of those represents a potential treatment failure. So, when you're facing this rising tide of resistance, what do? Well, the only real path forward is a smart, deliberate, and strategic effort to protect the antibiotics that still work. And that is the absolute core mission of antimicrobial stewardship. Now, stewardship isn't about just restricting antibiotics. It's about optimizing them. It's a whole series of smart moves. It's de-escalating from that empiric sledgehammer to a targeted scalpel the second you get the lab data. It's dosing intelligently to knock out the bug without causing needless toxicity. It's getting patients off IVs and onto pills sooner. It's using the shortest effective treatment course. And what powers all of this? Using better, faster diagnostics to guide every single one of those decisions.
And while it might not have that Hollywood blockbuster appeal, the real-world impact of good stewardship is so much more profound. It is a quiet, steady battle that's being fought in every hospital, on every ward, with every single prescription, all to protect one of the most important pillars of modern medicine.
And we're going to leave you with this question, because really, this is what it all boils down to. Unlike almost any other drug we use, taking an antibiotic for one patient has a direct impact on how well it will work for another patient down the line. They are a shared and finite resource. Every choice we make today is either a deposit into or a withdrawal from our collective power to cure.